Hello everyone. I'm from the technical support team at IDEC. Today, I'll be guiding you on how to create a PLC program for the FT1J and FT2J. If you haven't watched the tutorial video on creating an HMI program, please go back and check out part 1 first. Alright, let's get started. For how to access the software used to program the PLC, WindLDR, you can open it by double-clicking on Control Function Setting, or you can go to the View menu and select Control Function. Personally, I usually double-click from here. After you double-click, it will open the WindLDR software. Normally, the software will open to the Configuration tab, where you'll see your device listed. If you accidentally close this tab, you can access it by going to the Configuration menu and selecting Cartridges. That will open the Configuration tab again. In the Configuration tab, if you look at the bottom, it will show you the device addresses for your inputs. You can assign tag names or comments and see how many have been used, which you can check here. And for Q, which is the device address for outputs, you can see how many are available to use in this section. For the cartridges module, you can add 2 more slots at the back of the FT2J to expand with a few more digital or analog I/O. For the digital I/O cartridges, you can choose the card you want to add, like the FC6APN4, which is a 4-point input card. If you want to use it, just drag it and drop it, and you'll see that you now have 4 additional input points. Or the FC6APTS4, which is a transistor output card in source mode. If you want to add it, just drag and drop it, and you'll get 4 additional transistor source output points, from Q14 to Q17. For the analog I/O cartridges, like the FC6APJ2A, which is a 2-point analog input card, if you want to delete it, just click on the card and press the delete key on your keyboard. The card will disappear, and then you can drag a new card and place it in its place. For the analog input card, it will add AI6 and AI7, and these will have device addresses reserved, which you'll need to check in the manual. For this training, I won't be covering this part, so I'll go ahead and delete it for now. Next, for the function area setting, please click on Run, a stop control, and a pop-up for the settings will appear. The Run Stop control is commonly used to control the run or stop functions of the PLC. For now, I recommend leaving the settings at their default values. Next, for the memory backup, by default, the internal relay and shift register are set to clear all, but the counter and data register are set to keep all. This means that when the power is turned off and back on, the data register will retain its previous values. Next, for the input and output configuration, in the special input section, you can set it as needed. By default, it is usually set to normal input. For Group 1, you can configure it to use a single or 2-phase high-speed counter. Let's say I choose this one, then I can set it to either single-phase or 2-phase, depending on what I need. After that, just press OK to confirm the setting. For Group 2 to Group 5, you can only configure them as single-phase high-speed counters. This means you can set up to 5 channels in total. There are also other functions like catch input, interrupt input, and frequency measurement, which you can configure here. However, for this training, I won't be covering these functions. In the input filter section, you can set the filter for your inputs here. However, I won't be recommending how to use this feature for now. In the analog digital input section, for I12 to I15, by default, they are set to digital, but they can also be changed to analog. These share the same channels as the digital inputs. You can choose to set them as analog. In the filter section, you can configure the settings, and for the signal type, you have two options, 0 to 10 volts or 4 to 20 milliamps. In the data format section, the default setting is binary data, which ranges from 0 to 4095. For monitoring the stored values, the device address is D8040. To monitor the status, you can check D8042, which will show error codes or other status information. You can set the data format to an optional range, where you can configure the min and max values yourself. Typically, I set the min to 0 and the max to 1000. This means that when an analog input of 10 volts comes in, the value in D8040 will show as 1000, and when 5 volts come in, it will show as 500. I reference this using two decimal places, and you can use this setup as well. Moving on to the analog output section, this part can only be configured on models with transistor outputs. Models with relay outputs cannot be used for this purpose. You can set it to either 0 to 10 volts or 4 to 20 milliamps. Additionally, you can define the settings by selecting the optional range and specifying the min and max values. For example, I'll set it to 1000 units. The data will be located at device addresses D8044 and D8046 for the status. The analog input settings are configured in a similar way if you plan to use them. However, in this example, I'm not using them, so I've set everything to the default values. Next is the self-diagnostic section, where you can configure the watchdog timer. However, I recommend leaving it set to the default for now. Once you've completed the configuration, click the OK button to close the settings pop-up. As for the module configuration, the setup is quite straightforward. After completing this step, return to the main program screen. The main program tab is used for writing the PLC program. You can write your program within this area. On the left side of the program, you'll find features like the property window and the project window. At the bottom, there is the info window, which provides notifications if any errors occur. On the bottom right, you can zoom in and zoom out of your programming workspace. As for the configuration menu, I have already covered that earlier. Next, in the online menu, you can start or stop the PLC. You can also go to maintenance and issue a clear error command for any issues that occur. Additionally, you can click on Monitor to observe the PLC's real-time operation. If you'd like to test the program before actual use, you can click on Simulator for testing purposes. In the Setup section, you can configure the connection between your PC and the FT2J. You can set the connection parameters here. Next, in the View menu, under the Workspace section, you can choose the tools you want to display. If you want to use a particular tool, just check the box next to it. Personally, I don't often use the toolbox or the property sheet. Most of the time, I only use the tag editor, cross-reference, project window, and info window, these 4 tools. If any of them are closed, you can open them to match my setup. In the Show and Hide section, you can choose whether to display the device address in your program as a tag name or the device address. In the Number of Columns section, you can set the number of columns according to your preference. Right now, I have it set to 12, meaning there are 12 columns in my programming workspace. If you'd like to add or reduce the number of columns, you can adjust it here. You can adjust the font and text size here, as well as set the rung width and zoom level. Next is the Home menu, which is the main section we'll be using. It includes tools like copy and paste, which are commonly used tools. There's also new for creating subroutines, which are smaller programs. And with import, you can bring in other projects as well. Next, in the instruction section, you can use the select tool to choose instructions, or you can simply click with the mouse as usual. Next, in the basic instructions section, you'll find various basic commands for you to use, such as an O contact, NC contact, output contact, set, reset, and other instructions, all located in this section. Next, in the advanced instructions section, you'll find more advanced commands compared to the basic ones, along with special instructions that allow you to use a wider range of functions. Next, in the macro instructions section, you can create your own macros. The concept is similar to function blocks, where you write the program in advance and then you can call it and set the parameters as needed. In the line section, you can use draw line and eraser to draw or erase connecting lines in your program. You can draw lines both horizontally and vertically. I'll explain the details of this later on. This also includes functions like increment, decrement, invert, and adding wrong comments, along with various ways to insert, append, and delete elements in your program. You can also navigate to the bookmarks you've set. You'll need to set the bookmarks first. Doing this will make it easier for you to find specific parts of your program that you've bookmarked. You can find or replace device addresses in this section. For the converse program, it's used to check the program you've written to see if there are any errors. You can click here to perform the check. Next, before we start writing the PLC program, I'd like to introduce you to the various device addresses. For this part, I'll be referring to the manual, specifically the ladder programming manual. You can download it from the IDEC website. Then we'll look at the devices for the FT2J and FT1J models. In the device list, the input side uses the symbol I. For the FT2J, it ranges from I0 to I15, providing a total of 14 points. For the FT1J, there are 8 points available. For the expansion input, which is the cartridge module added at the back, it also supports up to 8 points. On the output side, the symbol used is Q. For the FT2J, there are 8 points available, while the FT1J provides 4 points. You can also expand with an additional 8 points, ranging from Q10 to Q17, like this. And one of the commonly used components is the internal relay, represented by the symbol, and each unit is a bit, and there are 6,400 points available for use. It's mainly used to assist with various aspects of programming. And then there's the special internal relay, also represented by M, starting from M8000 onwards. There are about 100 points available, each with its own specific functions. Next is the shift register, which has about 100 points available. I won't go into detail about it since it's not used very often. Next are the timers, which use the symbol T. They can be either bits or words, with 200 points available. Similarly, counters also have 200 points available, and then there are the data registers, represented by the symbol D, with a total of 4,000 points available. Additionally, the special data registers start from D800 onwards, with 200 points available, and the index registers, which are used for handling pointers, have 16 points available. Next, if you click on the special internal relay, you'll see details about what M8000 and each relay represent. If you scroll down further, there's a detailed explanation of how each special relay functions, as each one has its own specific purpose. Next, for the special data registers starting from D8000, they are used for various functions, such as the internal clock data, which provides the date and time. If you scroll down in the manual, You'll find the details of how each one works, and you can check the specifics there. This is how the devices are generally used. Next, I'd like to introduce you to the basic instructions, which are used when writing PLC programs. The first one is load and load not, which we commonly refer to as the NO normally open contact and NC normally closed contact. For the normally open contact, the function is that when it is pressed or activated, the status will be on. When it is not pressed or not activated, the status will be off. For the normally closed contact, by default, it will send an on status. However, if you press the button or activate it, it will send an off status. These two types, NO and NC, work oppositely from each other. Next, for the output, there are two types, the regular output and the output not. The regular output works by turning the output on when it receives an on status. For the output not, when an on status is received, it will send an OFF status to the device address that we've specified. It works oppositely to the regular output. The usage of the NO, NC contacts, and output coils works like this. Now, I'll show you an example program. If you look at the timing chart on the right, it corresponds with the example program here. In the example, we write IO as a NO contact, which is directly connected to QO, the output coil. For the other part, I1, which is a NO contact, is used to turn on Q1, the output not coil. Now, let's look at the timing chart for Q0. From the example program, Q0 will be on only when I0 is on. If I0 is on, Q0 will also be on. If I0 is off, then Q0 will be off as well. On the other hand, if I1 is on, Q1 will have an OFF status. Now, if you look at the timing chart, when I1 is on, Q1 will have an off status. But when I1 is off, Q1 will be on. You'll notice that as long as I1 is off, Q1 will remain on throughout. The timing chart for the operation will look something like this. Now, let's go ahead and write an example program. Now, back to the PLC programming software. Go to the basic section, and you'll find the normally open contact, or the shortcut key. If you can't remember the shortcut, you can click and select it from here, then click and place it in the area where you want to write the program. Alternatively, first, delete the contact you created earlier. Then, press the A key on your keyboard. A coil selection pop-up will appear, which is the shortcut for normally open. From there, press Enter or click OK to confirm. From this pop-up, you can select either normally open or normally closed. In the tag name section, you can assign your device address. For this example, I'll use I0. Alternatively, if you want to select a different device address, click on the three dots button. A pop-up will appear, allowing you to choose the device type you need from there. For now, I'll click Cancel to exit. You can add a comment in this section, but I won't add anything for now. After that, click the OK button. Next, for the output, if you're already in this section, you can go to the Basic tab and select the output option. Alternatively, you can type out on your keyboard and press Enter, which will bring up a pop-up window. After that, press Enter for the Out command. In the Type section, you'll see options like Out, Out Not, Set, and Reset. In the Tag Name field, you can assign your device address here. For this example, I'll set it to QO. Similarly, you can click on the three dots button to select the device type and device address you need from there. In the comment section, I won't add anything for now. Then, click OK. you'll notice that the coil or output will automatically be positioned on the far right side, which is the standard arrangement when writing programs in a ladder diagram format. Next, to create a new line for programming, you can simply press the down arrow key on your keyboard. This will automatically add a new line for you. Now, create another contact by pressing the A key on your keyboard, followed by the Enter key. In the tag name field, set it to I1. For the type, select Normally Close, and then click OK. Next, click on the far right side, then type out on your keyboard and press Enter. Set the tag name to Q1, and this time, select Out Not, then click OK. If you type in this zone, you'll notice that the connection line won't be automatically drawn. We have a tool called Draw Line for connecting the elements. If you're not familiar with the shortcut, I recommend using this tool. Simply click on it once, then click and hold the left mouse button to drag the line as needed. There's also a shortcut for this. You can hold down the Control key on your keyboard and then press the arrow keys to delete any lines you've drawn. For drawing lines, hold down the Shift key and press the arrow keys, and you'll be able to draw the lines. You can also draw lines up or down by holding down the Shift key and pressing the up arrow. To delete lines, hold down the Control key and press the down arrow. You can also use the left or right arrow keys to adjust the line position. Feel free to test drawing lines, either using the shortcuts or the drawing tool, based on what works best for you. In the example, once you've finished drawing the lines, let's test the simulation. Go to the online menu and then select Simulation. You will notice that Q0 is off initially. If you turn I0 on by double-clicking it or pressing the Enter key on your keyboard, then Q0 will turn on as well. If I0 is off, Q0 will also be off. In this example, I made a small mistake with I1. Please stop the simulation for now. Then, change the I1 contact to Normally Open, as shown in the example, and click OK. One more thing, for the shortcut to toggle between an O and C contacts, you can press the slash key on your keyboard to switch between the two. Alternatively, you can press the plus or minus key on your keyboard to adjust your device address up or down. Now, I will change it to I1 and set it as an O contact. After that, click on the simulation button again to test. For the I1 contact, if you don't press it, Q1 will stay on. However, if you activate the I1 contact, Q1 will turn off. The symbol for I1 works oppositely to the output coil. If you're unsure about the symbols, you can go to the batch option. This will bring up the batch monitor pop-up for you. In the device section, select Q. You'll see that when I1 is off, Q1 will be on, with a status of 1. However, when I1 is on, Q1 will turn off, showing a status of 0. Viewing through the batch monitor will make the status clearer. This is how the out-not function works. After that, click Simulation to exit, and then return to the Home tab. For the next instruction, I'll introduce the set and reset instructions. If you write a sample program based on this diagram, it works like this. I0 triggers a set for Q0, and on another line, I1 triggers a reset for Q0. You can refer to the timing chart on the right. When you turn on I0 just once, there's no need to keep it on. Q0 will stay on continuously from that point onward, until you turn on I1, which triggers the reset command for Q0. Looking at the timing chart, as soon as you turn on I1, Q0 will immediately change its state to stay off continuously. That's basically how the set and reset commands are used. Now, let's try writing a sample program to see how it works. Back in the WindLDR program, use your mouse to select your old program first, then press the delete key on your keyboard to remove it. After that, type the following, pressor, and then press enter. Next, type IO in the tag name field, using it as a normally open contact. Then, press OK or enter on your keyboard. For the set command, you can simply type set directly on your keyboard. If you can't remember the command, you can go to the basic menu and select the set instruction, which works the same way. However, I'll recommend a shortcut. Just type set on your keyboard and then press enter. You'll notice that the type is automatically set to set. In the tag name, enter Q0 as shown in the example, and then press OK. For the next line, press O on your keyboard and then press enter. In the tag name, enter I1 and press enter again. Next, for the reset instruction, you can type RST on your keyboard. If you can't remember it, you can go to the basic menu and select the reset instruction instead. I'll use the shortcut method by typing RST and then pressing enter. In the tag name, enter Q0 and press enter again. Next, try running the simulation by going to the online menu and then selecting simulation. Since I1 is still on from the previous simulation, double-click to turn it off first. After that, you can try opening the batch monitor, and you'll see that Q0 is currently off. Alternatively, you can monitor it by selecting Custom Monitor, and then setting the address to Q0. This is how you can monitor it like that as well. Next, set the monitor type to bin. If you turn on I0, you'll notice that Q0 will turn on or have a value of 1, even after you turn off I0. Q0 will still remain on. Next, if you turn on I1, it will reset Q0, which will cause Q0 to stay off or have a value of 0. If you turn on I0 again, it will set Q0 to 1 and keep it on, which can be reset by turning on I1. This is how the set and reset instructions are typically used. After you've finished the simulation, be sure to close it. Next, I'll introduce how to use the and not instructions. For the and instruction, we write to contacts in series, and there will be one output. To read the ladder logic, Q0 will be on only when both I0 and I1 are turned on at the same time. If one of them is on but the other isn't, Q0 will remain off. This is how the AND logic is written. In the first row, let's look at the example in the timing chart. Suppose I only turn on I0. Q0 will not turn on until both I0 and I1 are on at the same time. Then, when I0 turns off and only I1 is on, Q0 will remain off. The condition for Q0 to turn on is when both I0 and I1 are on together. Next, let's look at another line, which is also an AND instruction, but this time, I1 will be a normally closed contact. The condition for Q1 to turn on is when I0 is on and I1 is off. Only then will Q1 have an on status. Next, let's look at the timing chart. When I0 is on during this period, and I1 is off, Q1 will be on only during this specific period when I0 is on and I1 is off. For all other conditions outside of this, Q1 will not turn on. This is an example of how the AND instruction works. Next, we will try writing the program for real. Please return to the WindLDR software. After that, delete the previous program you wrote before starting the new one. Next, try typing the program as shown in the previous example. Press O on your keyboard and then press enter. For the tag name, enter I0 and press enter. Next, press O on the keyboard again, then press enter. For the tag name, enter I1 and press enter. Then, type out on the keyboard and press enter. For the tag name, enter Q0 and press enter. For the next line, you can copy the previous ladder program. Use the mouse to select the ladder program from the previous line, then press Ctrl+C on your keyboard. Click on the next line and then press Ctrl+V to paste it. You can then click on I1 and press the / key on your keyboard to switch between normally open and normally closed, which is the shortcut key for this action. For the output Q0, you can press the + key on your keyboard to increment the device address by 1. This will help speed up your programming process. Next, try running the simulation to see how it works. Open the custom monitor. Here, enter I0 and I1 in one section, and in another section, enter Q0. For the monitor type, select bin, and add Q1 as another item to monitor. When you turn on I0, the current value will be 1. Then, when I1 turns on, Q0 will be on as well, meaning its value will be 1. That's right, if either one of them is off, Q0 will immediately be off as well. This demonstrates how the AND condition works. Next, I'll turn off I0 and I1. In another line, it will also be an AND condition, but this time, I1 will be a normally closed contact. Q1 will be on only when I0 is on and I1 is off. Right now, I1 is off. When you turn on I0, Q1 will immediately turn on. If I0 is off, or if I1 turns on, the status of Q1 will immediately turn off. The AND instruction works under these conditions. Now, please close the pop-up monitor and exit the simulation mode. In the next section, I'll explain how to write the OR and or NOT instructions. The principle for writing OR is that we arrange them in parallel. This means you place I0 at the top, and then I1 is written in parallel with it, and then connect it to the output, which in this case is Q0. For example, if you turn on I0 by itself, the signal will flow from left to right, and your Q0 will turn on immediately. Similarly, if you turn on I1, the program will follow this path, and your Q0 will also be able to turn on. In summary, if any of your contacts turn on, your output will also turn on. This is how you write an OR instruction. Next, let's take a look at the timing chart. When I0 is on during this period, Q0 will also turn on during the same period. Similarly, when I1 is on during this period, Q0 will turn on as well. You can observe that as soon as either one turns on, Q0 will immediately turn on. Next, let's look at the program for the output Q1. When I0 turns on, Q1 will turn on immediately. Alternatively, when I1 turns off, Q1 will also turn on. Take a look at the timing chart. When I0 turns on during this period, your Q1 will also turn on. And during the period when I1 is off, which is this section here and the following part, Q1 will also turn on. Let's try writing an actual program together. This will help you gain a better understanding of how to use this instruction. First, select the entire old program, and then delete it. Next, let's start writing the program. Press the A key on your keyboard, then press Enter. In the tag name field, enter I0, and press Enter. For the next line, press the A key again, press Enter, and set the tag name to I1, then press Enter. Now, click on the far right section, type out on your keyboard, and press Enter. In the tag name field, enter Q0, then press Enter. Next, I'll show you how to draw lines. Hold down the Shift key on your keyboard, then press the up arrow to draw a line from the bottom to the top. Next, keep holding the Shift key and press the right arrow to draw a connecting line between the contact and the output. Next, go to row 3. Press the down arrow once to create row 4. Now, I will copy the program from above by pressing Ctrl+C. Then go to row 4 and press Ctrl+V to paste it here. For I1, you can press the / key on your keyboard to change the contact to normally closed. For the output Q0, press the + key on your keyboard to change it to Q1. These are shortcuts that will help make the programming process easier. Now, let's try running the simulation. Next, go to Custom and select New Custom Monitor. Then, in the Device section, enter I0, I1, Q0, and Q1. For the monitor type, choose bin. At this point, I0 is on, but I will turn it off for now. Please observe the Q0 output. When I0 is on, you will notice that Q0 turns on immediately. Similarly, if I1 is on, Q0 will turn on as well. This shows that as soon as any one of the inputs turns on, our output will turn on immediately. That's how it works. For the other part of the program, when I0 is on or I1 is off, Q1 will be in the on state. In this case, since I1 is off, which is 0, Q1 will turn on. However, if I1 is turned on or has a value of 1, Q1 will be in the off state. But if I0 turns on, Q1 will turn on. This is the general way your instruction works. Now, please close the monitor window and stop the simulation. In the next section, I'll introduce how to use timers. For the FT2J, there are 4 timers: TML, TIM, TMH, and TMS. If you want to remember just one shortcut, you can remember TML. The TML timer increments by 1 second at a time. The next timers are TIM, which increments by 100 milliseconds, TMH, which increments by 10 milliseconds, and finally TMS, which increments by 1 millisecond. Next, let's look at the timing chart. TML is the 1-second timer. If we use the TML instruction and set the parameter to 4, when I0 is on for 4 seconds, T0, which is the device address of the timer, will turn on. Take a look at the timing chart. If we keep I0 on for 4 seconds, T0 will turn on. If I0 turns off, T0 will turn off as well. However, in this part, we've added an additional condition. I1 and T0 both need to be on for Q0 to turn on. Next, TIM can be used similarly. If you set the parameter to 20, the timer will increment by 100 milliseconds, and it will function in the same way as TML, but with a shorter time period. The 100 millisecond count works similarly to shifting the decimal point by 1 place. For this example, it would be 2 seconds. When we keep I0 on for 2 seconds, T1 will turn on and will turn off when I0 is 0. Next, for TMH, which is a 10 millisecond timer, if we set it to 100, it will be equivalent to 1 second, as shifting the decimal point by 2 places gives us the value of 1 second. Looking at the timing chart, if we press and hold I0 for 1 second, T2 will turn on. Next, for TMS, which is a 1 millisecond timer, in this example, we'll set the parameter to 500. This means the timer will count for 500 milliseconds, or half a second. Each timer differs only in the resolution of the counting. In general, the usage of timers works this way. Next, I'll show you a real program example to demonstrate how to write the ladder program. Let's go back to the WindLDR software. First, delete the old program you had written earlier. Then, write a new example by pressing the A key on your keyboard and then pressing Enter. In the tag name field, enter I0 and press Enter. Next, type TML on your keyboard. which is the 1-second timer. Alternatively, you can go to Basic, then to Timer, and select TML that way. Next, place the TML timer at this location. Next, double-click on the TML timer. In the tag name field, enter T0. For the preset, in this example, set it to 5 seconds. Then, click OK to confirm. The timer can be used in two ways. One way is to directly write the output after the timer. For example, you can type out on the keyboard right after the timer. In the tag name field, enter Q0, then press enter. This way, when you hold I0 on for 5 seconds, Q0 will turn on. You can write it like this directly in the program. Alternatively, you can write it this way. For example, you can copy the line and paste it in row 2. Then, press the plus key on the keyboard to change it to I1. For this one as well, press the plus key to change it to T1. For the next line, you can write it this way. Press the A key on your keyboard, then press enter. In the tag name field, enter T1, then click OK. After that, type out on the keyboard, press enter, and enter Q1 for the tag name, then press enter. This way, you can either use the contact from the TML timer here, or you can directly connect the TML timer to the output. Both methods are valid. Now let's try the simulation. For example, if I turn I0 on, the TML timer will start counting down continuously until it reaches 5 seconds, and Q0 will turn on. If I turn I off, Q0 will turn off immediately. If we turn I0 on but don't keep it on for the full 5 seconds before turning it off, you'll notice that Q0 will not turn on. For this one, it's similar, just with a different ladder program structure. If you turn I1 on, the TML timer T1 will start counting down. Once it completes, T1 will turn on, which will also turn on Q1. You can write the program in this way as well. In general, this is how you use timers. For other timer instructions, you can double-click on your TML timer to open the settings. Here, you can select the resolution for your timer, such as TIM, TMH, or TMS. You can adjust the resolution from this point. The usage is the same, but the only difference will be the resolution. The next thing I'd like to introduce to you is TMLO, or the timer off delay. This command is quite similar to the timer on command. If you're trying to remember the shortcut, all you need to remember is just TML for now, and you can select the specific option later. And for the increment part, it works the same way. Next, let's take a look at the functionality of TMLO. Its operation is quite similar to TML. For example, if we set the parameter to 4, when you turn on I0, T0 will turn on immediately. However, when you turn off I0, meaning you change it from on to off, T0 won't turn off right away. Instead, it will delay for another 4 seconds before switching to the off state. This is the main difference when using the timer off. It's designed specifically to delay the off state. For others like TMO, they function in the same way but differ in the timer's resolution. For example, TMSO has the highest resolution, which is 1 millisecond. Next, go back to the WindLDR software, and we'll write a sample program for the timer off function. If you can't remember the command, you can go to the Basic tab, then Timer, and select TMLO from there. Alternatively, if you're already using TML, you can adjust the delay setting to select Off Delay, and your command will automatically change to Timer Off TMLO. I'll use the same one and just modify it to Timer Off TMLO. For another example, I'll do the same, change it to Delay Off and then click OK. After that, Try running a simulation. The operation will be similar. When you turn I0 on, Q0 will turn on immediately. Then, when you turn I0 off, it will delay for 5 seconds before Q0 turns off. This is a common use case for the timer off function. Once you've finished testing, close the simulation. Next, I'll introduce the counter commands to you. There are 3 types of counters: CNT, which is an adding counter; CDP, which is a dual pulse reversible counter; and CUD, which is an up-down selection reversible counter. For CNT, which is the most commonly used command, you can set the counter's device address. In this example, we'll set it to C0. Then, you can define the target count. For instance, in this example, we'll set it to 5. The CNT command has 2 inputs. The first one is the reset input, and the second one is the pulse input, which is responsible for counting values for the counter. In the example, I0 will be used as the reset input, and I1 will be used as the pulse input. When you turn I0 on to reset, the value in counter CO will reset to 0. Next, when you turn I1 on, which is the pulse input, and then turn it off once equal to 1 pulse, the counter will count up to 1. If you send another pulse by turning I1 on and off again, it will count up to 2. If you repeat the process, it will count up to 3, and so on, until it reaches the set value, which in this case is 5, as you defined earlier. When C0 reaches the set value of 5, it will turn on. Even if you continue sending pulses, the counter will not count higher than 5. Once it reaches 5, C0 will remain on until the reset is triggered. When you turn I0 on, which is the reset input, the value in counter C0 will be reset to 0, and the counter will turn off. This is how the counter is typically used. Next, we have the CDP command. I'll just give a brief introduction since it's not used as often. This counter has 2 inputs. One for the up pulse, which counts upwards, and another for the down pulse, which counts downwards. This counter allows you to count both up and down. The next command, CUD, is quite similar. It has I1 as the pulse input, which is used for counting, and I2 as the up-down selection input, which determines the counting direction. When I2 is on and you send a pulse by turning I1 on, it will count upwards. If you turn I2 off and send a pulse by turning I1 on, it will count downwards. This is the basic way this counter works. Now, let's go back to the WindLDR software and try writing a sample program to implement the actual usage. First, delete the previous program you wrote. Then, go to the Home menu, select Basic, and then go to Counter. After that, choose CNT. If you remember the shortcut, you can simply type CNT on your keyboard. I'll click and paste it here. You'll notice that there are the reset and pulse inputs. First, double-click to open the pop-up settings window. For the counter command, you can choose from 3 types, as I mentioned earlier. You can also select the data type, either word or double word, depending on your needs. Set the counter to C0 for now, though you can choose other numbers as needed. In this example, I'll set the preset value to 5. After that, click OK. Next, add the reset input. Type on the keyboard and press Enter. Then set I0 as the tag name and press Enter again. For the pulse input, I'll copy and paste it here. Then press the plus key on the keyboard to change it to I1. In this example, I'll connect the coil output directly to the counter's output. Type out on the keyboard and press Enter. For the tag name, I'll set it to Q0 and then press Enter. You can write the program like this. Next, try running a simulation. Go to the online menu and select Simulation. At this point, you'll see that the value of C0 is 0. When you turn I1 on, the counter value for C0 will count up to 1. After that, turn I1 off. Then, try turning I0 on and off again. The counter value for C0 will change to 2. If you turn I1 on and off again, it will become 3, then 4. When you turn I1 on for the 5th time, C0 will reach 5, and the Q0 output will turn on, meaning the counter has counted up to 5. If you try turning I1 on again, you'll notice that the counter value for C0 won't increase anymore. No matter how many times you turn I1 on, the counter will remain at the maximum value that was set, which in this case is 5. If you want to reset the counter value, simply turn I0 on. Once you turn it off, the value in counter C0 will be reset to 0. After that, exit the simulation mode. The counter works similarly to the timer. You can use the counter as a contact as well. For example, type on the keyboard and press Enter. Then set the tag name to C0 and press Enter. You can then use the C0 contact in your ladder program. This is how you can use the counter in this way as well. The next part I'd like to introduce is SOTU and SOTD, which stand for single output up and single output down. This is a command that makes the output from the previous instruction turn on for only a single pulse. For example, when we turn on I0, it will trigger Q0 to turn on for just one pulse. In other words, it stays on for only one scan cycle of the PLC. For example, in this program, we wrote I0 SOTU to Q0 and I0 SOTD to Q1. Next, take a look at the timing chart. Suppose I turn on input I0 and keep it on, you'll see that Q0 will turn on for only one pulse, or one scan time, and then turn off immediately, even though I0 remains on. Until I0 turns off, the SOTD will activate, which is the falling edge pulse. This means Q1 will turn on at the falling edge for one pulse and then turn off. Similarly, if you turn on your I0 again, which generates a rising edge pulse, your Q0 will turn on for one pulse, or one scan time, and then turn off. Likewise, if you turn off I0, it will work the same way. That means your Q1 will turn on for one pulse, or one scan time at the falling edge of I0. The usage of the SOTU and SOTD commands works roughly like this. Now, go back to the PLC software. Then select the program you wrote earlier and delete it. For this example program, there might be some commands that I haven't introduced yet. I'll write them out as an example first. Type on the keyboard, then press Enter. For the tag name, enter IO, and then press Enter again. Next, type add on the keyboard, which is the addition command. I haven't gone into the details of this command yet. For S1, enter the value D0, and for S2, enter the value 1. For D1, enter the same value as D0, then press Enter. For the next line, copy the first line and paste it into the second line. Then, I'll press the plus sign on the keyboard to change it to I1. Then, click the mouse on S1, and press the plus sign on the keyboard. Your D0 will change to D1, and for D1, press the same button to change the value to D1. Type SOTU on the keyboard, which is this command, and then press OK. If you can't remember, go to the Home menu, then select Basic, and choose the Single Output command. You will find SOTU and SOTD there for you to use. Next, go to the Online menu and select Simulation to test the operation. Next, try turning on I0, and you'll notice that the value in D0 changes very quickly. This means that with every scan cycle of the PLC, D0 is being incremented by 1 and stored back in the same D0. As a result, the value keeps increasing, which is not what we want. What we want is to turn it on just once and perform the addition only once, so we need to use SOTU as well. For example, when I turn on I1, the value in D1 will become 1. After I turn I1 off, then turn it on again, the value in D1 will become 2. If I turn it off and then turn it on again, the value in D1 will become 3. You can use SOTU to prevent the add command from executing incorrectly. In this example, we want it to add only once when you turn on I1. So we need to use SOTU to ensure the command works as we want. This example will help you understand how to use SOTU and SOTD more clearly. Once you've finished testing, go ahead and close the simulation. In the next part, I'll have some questions and a sample program for you to try programming, so you can test out our FT2J. Alright, let's take a look at the task first. Example program, Dual Motor Control System. 1. Motor 1 Control. Pressing Start 1 M1 will activate Motor 1 Q1 for the duration specified in D1. Pressing Stop 1 M2 will immediately stop Motor 1 Q1. Motor 2 Control. Pressing Start 2 M3 will activate Motor 2 Q2 for the duration specified in D2. Pressing Stop 2 M4 will immediately stop Motor 2 Q2. Mutual exclusivity. Only one motor can operate at a time. If one motor is running, the other cannot be started. Maintenance lock. If either motor completes 10 operating cycles, the corresponding maintenance indicator light maintenance 1 Q3 for motor 1 or maintenance 2 Q4 for motor 2 will turn on. The affected motor cannot be operated again until the corresponding reset button reset 1 M5 or reset 2 M6 is pressed. Let's get back to the program we're using to write the PLC. First, delete the old program. Next, when it comes to writing the new program, since we already know what we need to write, I'll start by assigning comments first. Go to the Tag Editor tab. If you don't see it, go to the View menu and open the Tag Editor from there. I'll assign comments to the various devices first to make them easier to reference later. Start by going to the device type, then to M or internal relay. In this case, we'll use it as a substitute for a button, which I'll later configure on the HMI side. Next, I'll assign comments to the device addresses we'll be using. Based on the task we have, M1 will be labeled Start 1, and M2 will be Stop 1. Then we'll have Start 2 and Stop 2, along with reset buttons for Reset 1 and Reset 2. That's about all we'll use for M. For another part, go to Device Type and select Q, which is our output. The addresses we'll use include Q1 for motor 1, Q2 for motor 2, Q3 for maintenance 1, and Q4 for maintenance 2. These are the device addresses we'll use for this task. Now, let's start writing the program. First, we'll start by creating a contact. Type A on your keyboard and press Enter. Then type M1 in the tag name, which corresponds to the Start 1 button, and press Enter. When you press M1, it will activate the output. To do this, type out and press Enter. Then set the tag name to Q1, which represents motor 1, and press Enter. To keep the motor running after pressing the button, we need to use a self-holding circuit. This involves using Q1 your output as a contact to lock the circuit. To do this, press A and then Enter, type Q1 and press Enter. Next, hold Shift on your keyboard and use the up arrow to draw a connecting line. If you program it this way, pressing L1 will activate Q1, and the Q1 contact will stay active, keeping the circuit locked. To stop the circuit, we need to use the Stop button, which is M2. Press A on your keyboard and press Enter. Choose Normally Closed, as it will break the circuit. Set the tag name to M to the stop button and press OK or Enter. Now, your circuit can be stopped by pressing M2, the stop button. Next, if we want the motor to run for a specified amount of time, we'll use a timer. This is done by creating a parallel output branch. First, click to leave one space and type TML timer 1 sec. If you don't remember the command, you can go to the basic section and find the timer there. Press Enter, and for this example, let's name it T1. Set the preset value to D1, which will be our timer's value, and press OK. To make both outputs run simultaneously, hold Shift and press the down arrow to draw a parallel connection. After the timer finishes, it needs to break the circuit. This is similar to how we set up the stop button. Click to add a new contact, type A, and press Enter. Choose Normally Closed, and set the tag name to T1, the timer we created. Press OK. Before proceeding, test your program by going to Online and selecting Simulation. First, set the value of D1, which is currently 0. Double-click the timer and set D1 to a value, let's say 5, and press Enter. Close the timer settings. Now, when you turn on M1 and turn it off, you'll notice the motor runs for 5 seconds before stopping. If the motor is running and you press the stop button, the motor will stop immediately. That's how this circuit works. Once tested, exit the simulation to continue writing your program. Next, let's program for motor M2. Click on the second line, then press Enter on your keyboard to separate the rungs of the program. After that, select the first rung by dragging to highlight it, and press Ctrl+C to copy. Paste it onto the second rung, as the programs are similar. You can press the plus key on your keyboard to update the elements. For example, change M1 to M3 start to button and press the plus key twice to change M2 to M4. Similarly, update Q1 motor 1 to Q2 motor 2 by pressing plus, and do the same for the self-holding contact to set it to motor 2. For the timer, press plus to change it to timer 2. However, you also need to update the internal parameters. Double-click the timer, rename it to timer 2, and change the preset value to D2 for the second timer. Press OK to confirm. Don't forget to also update the contact associated with the timer to T2 by pressing plus. Now you have two circuits controlling motor 1 and motor 2 separately. The next task requires ensuring that when one motor is running, the other cannot start. This is achieved using an interlocking circuit. The method involves using the output of motor 2 as a contact for motor 1, and vice versa, to prevent simultaneous operation. Here's how to do it. 1. Click the desired location in the first rung. Press A on your keyboard and then Enter. Select the contact type as normally closed. Set the tag name to Q2 motor 2's output and press OK. This blocks motor 1 if motor 2 is running. 2. Do the same in the second rung. Press Enter, choose normally closed, and set the tag name to Q1 motor 1's output. Press OK. Now, test your program with the simulation mode. Double-click the timers to set their preset values. For example, set D2 to 5. Then, run motor 1 and try starting motor 2. You'll notice that motor 2 cannot start until motor 1 has stopped. This is the effect of the interlocking circuit. Finally, stop the simulation to proceed with the next steps. Next, the task specifies that when a motor completes 10 cycles, it will no longer operate unless you reset it first. To implement this condition, you can use a counter. Start by pressing Enter to create a new rung. Click on the second slot in the new rung and type C and T, which stands for adding a counter. If you can't remember the command, go to the Home menu, select Basic, and choose the counter from there. Then, press OK. Let's set the counter as C1 for now, with a fixed preset value of 10, meaning it will count up to 10. Press OK to confirm. Since we need two counters for this task, copy the existing counter by pressing Ctrl+C, move down a line, and paste it with Ctrl+V. Double-click the second counter to edit it, and set it as counter C2. For this setup, we'll use a simple condition. When Q1 motor 1 operates, the counter starts counting. Press Enter, and set the tag name to Q1 for the first counter. For the second counter, set it to Q2 motor 2. Copy the reset input and assign M5 reset 1 to the first counter by pressing Enter, and setting the tag name to M5. Do the same for the second counter but assign M6 reset 2. Copy and paste as needed, then update the tags accordingly. Once the counters are in place, you need to block the motor when the counter reaches its limit. The concept is that when the counter reaches 10, the motor cannot start. To achieve this, create a blocking circuit. Click on the location where the block should be added, press Enter, select Normally Closed, and set the tag name to C1 for the first motor. Repeat the process for the second motor by copying the block, pasting it, and updating the tag to C2. With this setup, the motor will stop functioning when the counter reaches its limit. To test, go to Simulation, set the timer value, for example, D1 to seconds, then start the motor. Observe that the counter increments by 1 each time the motor cycles. Hold the Start button to let the motor run 10 times. Once the counter reaches 10, you'll see that the motor is blocked and cannot operate until you reset it. This example demonstrates how to implement the counter logic in the circuit. Once the simulation is complete, stop it, and we'll proceed to program the HMI interface for integration with the circuit. Next, let's go back to the NV4 software, which is used for creating HMI screens. Now, we're going to design the screen for this section. First, go to page 1 and delete all the objects there. Open page 1 by double-clicking on it, then press Ctrl+A on your keyboard to select everything, and press Delete to clear all objects. After that, go to page 2 and do the same thing, press Ctrl+A and then Delete. For page 3, there's nothing to worry about. Finally, go to page 100, which is our template. Now, let's go back to page 1. When designing an HMI screen, I usually start with the standard objects like buttons or lamps and test the functionality first. Once everything is working correctly, I'll refine the design and make it look better later. First, we'll draw a button. Go to the Buttons section and select it button. Then, draw the button in the desired area. Adjust its size as needed. After that, double-click on the button. For action mode, select Momentary. Under Destination Device Address, click on the 3 dots button, and in the target, choose Control Device to use the PLC's device address. For the device type, we'll use M, which is an internal relay. You'll see the device addresses you've commented on, ranging from M1 to M6. Let's start with M1 and click OK. Next, go to the Registration Text tab, and in the text box, set it to Start 1. We'll focus on decorations later, so for now, just click OK. Now, hold Ctrl on your keyboard, and use your mouse to drag the button to create a copy. You can also hold Shift to keep the alignment straight while dragging. Double-click the copied button, go to Destination Device Address, click the three dots, and select M2, click OK, then go to the Registration Text tab, and change the text to Stop 1. Click OK again. Now, you should have two buttons. Select both by dragging your mouse over them, hold Ctrl, and drag them to create duplicates. You can also hold Shift to keep them aligned. This time, let's create two more buttons. Double-click the first new button, change the destination device address to M3, and set the text to Start to. Click OK. For the second button, double-click it, change the address to M4, and set the text to Stop to. Click OK. You'll still need to create two reset buttons. Select the last two buttons, hold Ctrl and Shift, and drag them downward to duplicate them. I'll place these a bit lower. Double-click on the first reset button, click the three dots for the address, and select M5 for reset 1. Click OK. Then go to Text and set it to reset 1. Click OK. For the second button, double-click it, select M6 for reset 2. Click OK, and change the text to reset 2. Click OK. Now we have all our buttons set up. The next step is to create the lamps, which will serve as our outputs. We'll have a total of 4 lamps: Motor 1, Motor 2, Maintenance 1, and Maintenance 2. Start by selecting lamps, then choose Pilot Lamp. Draw the lamp in the desired area. I'll place it here for now. Next, double-click on the lamp you just added. Go to the Trigger Condition tab. Under Lighting, set the trigger type to While On. For the device address, click the three dots. In the target, select Control Device, and for the device type, choose Q, which represents the output. Now, select Q1, which corresponds to Motor 1. Click OK. Next, go to the Registration Text tab, and in the text box, type Motor 1 for now. Click OK, and then adjust the size of the lamp to make it suitable. Next, copy the lamp by holding Ctrl and Shift on your keyboard, then drag and drop it to duplicate. After that, double-click on the new lamp and go to the Trigger Condition tab, just like before. Click the three dots and select Q2, then click OK. Go to the text section and change it to Motor 2, then click OK. Now, let's create the maintenance lamps. First, click on Motor 1, then hold Shift on your keyboard and click on Motor 2 to select both lamps. After that, hold Ctrl and Shift on your keyboard, and drag both lamps down to place them below. Double-click on one of the lamps, go to the Trigger Condition tab, and click the three dots. Select Q3, which corresponds to Maintenance 1, then click OK. Go to the text section and change it to Maintenance 1, then click OK. As for any text that extends beyond the lamp object, we'll fix that later. Next, double-click on the lamp, then go to the Trigger Condition tab. Change the device address to Q4, which corresponds to Maintenance 2, and click OK. Then, go to the text section and change it to Maintenance 2. Click OK again. At this point, the lamp configuration is complete. Next, we'll set up another component for inputting values into the device address, which is the D data register of the PLC. This is used for setting the timer values. Go to Data Display and select Numerical Input. Draw it in the desired area, then double-click on it. Go to the Destination Device Address section and click the three dots. Set the target to Control Device and the device type to D, which is the data register. You'll see various addresses for the data register, though we haven't added any comments for them yet. We'll have D1 and D2, which are the timer settings for the timer. You can select them here. Start by selecting D1, then click OK. For the other settings, leave them as the default for now, we'll adjust them later. After that, click OK. Next, hold Ctrl and Shift on your keyboard, then drag to duplicate the object. Double-click on the new one and change it to D2. You can make the changes directly from here. Once done, click OK. For these objects, which I didn't align evenly, I can fix that by selecting all 4 of them by dragging the mouse over them. Then, go to Arrange, select Align, and choose Align Left. This will align them all to the left evenly. Next, let's try a simulation test. First, go to the online menu and select Simulator. It will prompt you to save your work first. Just click OK to save. Once the simulator window opens, go to the top right corner and select WindLDR Simulation. This ensures the simulation works for both the PLC and HMI together. Click it once, and the software will also simulate the PLC side. Next, try setting timer 1D1 to 5 seconds and press Enter. For timer 2, set it to 2 seconds and press Enter. Now, try starting the system. When you press Start 1, motor 1 will start running. After 5 seconds, it will stop. If you try starting it again and then try to start motor 2, it won't work because motor 1 is already running. Similarly, if you start motor 2, motor 1 won't start until motor 2 has stopped running. For the scenario where the motor runs 10 times, I'll set timer 1 to 1 second for faster testing. Start the system and run it for 10 cycles. You'll notice that the lamp does not turn on. The reason the maintenance lamp doesn't turn on is that I haven't written the output for this lamp in my PLC program yet. This shows how simulation can help you identify errors in your program before using it in a real application. Next, close the simulation and click OK. Next, we need to go back to the PLC program and add more code. Specifically, we need to add 2 outputs for maintenance 1 and maintenance 2. Start by typing out on your keyboard right after the counter. Then press OK or Enter. After that, click the 3 dots and set the device type to Q output. Select Q3, which corresponds to maintenance 1, and click Close to exit. Then, click OK. For the second output, I'll just copy the first one. Select the section by dragging over it, then press Ctrl+C, click where you want to paste it, and press Ctrl+V, click on the output coil, and press the plus key on your keyboard once to change it to Q4. Now, when the counter completes its count, the maintenance 1 and maintenance 2 lamps will turn on. Finally, go back to Software and V4 and run the simulation again. Don't forget to click OK to save. After the simulator software opens, select WindLDR Simulation. The counter will still have the value from the previous simulation, so press the reset button first to restart the count. Then, set the timer to 1 second and press Enter. After that, press the Start button. Once the motor has been started 10 times, you won't be able to start the motor again. The maintenance lamp will turn on, indicating that maintenance is required for the motor. After performing maintenance, press the reset button to clear the counter, allowing the motor to operate again. The functionality we've set up is working as intended. Next, we'll move on to enhancing the design and making it visually appealing. I'll guide you through that in the next steps. For now, close the simulation, click OK, and return to the HMI screen. Next, I'll show you how to make the HMI interface look more visually appealing. First, let's adjust the buttons. Hold down the Shift key on your keyboard. Then click on the Start 1 button and the Start 2 button. This will allow you to select two objects at the same time. Then, double-click on the button. Go to the View tab and find Image type. I'll select Standard here. For the image, I'll use this default one. If you don't want to use it, click the Browse button to choose an image of your choice. I'll close this window since I'm sticking with the default. For the color in the off state, I'll set it to green. You can pick the color from this menu, and I'll select this particular shade of green. For the background color, I'll use white. Next, click the On button to see how it looks. I'll adjust the foreground color to the same green and keep the background color white. So when the status is on, it will display this style. After that, click OK. Now, the button will change to the colors I set green and white. Next, let's do the same for the Stop 1 button. Hold down Shift on the keyboard, then click Stop 1 and Stop 2 to select both objects. Double-click to open the settings. For the foreground color, I'll change it to red, and the background color will be white. For the on state, I'll keep the foreground color red and the background color white. Test it by toggling off and on to see the result. If you're happy with the colors, click OK. Finally, let's adjust the Reset button. Again, hold down Shift, click the first and second reset buttons, and then double-click on them. I'll set the foreground color to blue and the background color to white. For the on state, I'll choose the same blue for the foreground color and white for the background color. Toggle between on and off to see how it looks. Once you're satisfied with the colors, click OK. That's it, your buttons are now fully customized. Next, let's move on to Motor 1 and Motor 2. Start by clicking on one of them. Then hold down the Shift key on your keyboard and click the other one to select both objects at the same time. Once selected, double-click to open their settings. For the lamp, I'll set the image type to picture. After that, click Browse, and in the drop-down menu, choose the new category that we created earlier. For this example, I'll create a new image for you. Go to Symbol Factory, then use the search bar to type in motor and press Enter. This will bring up motor images. I'll select this one for the motor. Next, click Default All once. You'll notice the background is still blue. To change it, click on Background, then pick any color that's not already in the image. For example, I'll select this pink color. Once selected, click OK, and the background of your image will change to pink. Now, double-click the image again and give it a name. I'll name it motor_off. Then, check the color exchange box. Under From, click the color bar and select the color you set as the background pink in this case. After that, click OK. For 2, select transparent color, and then click OK again. Now, you'll have your motor_off image ready. Click on the image, and you'll see that it no longer has a background. For the on state, repeat the process, click Browse, go to the drop-down menu, and select the new category we created earlier. This ensures the image stays in the same folder. Then, click Symbol Factory, search for motor again, and press Enter. Choose the same motor image as before. This time, under Fill Color mode, change it to Shaded. For the fill color, click on the color bar and select green. I'll use this green as an example. Double-click the image and name it motor_on. Again, check the color exchange box. Set from to the same background color as before, pink, and to transparent color, then click OK. Now, Your motor underscore on image is ready. Click Select and test toggling between the on and off states to ensure everything works as expected. Finally, click OK, and you're all set. Next, let's adjust the lamp maintenance settings. Start by clicking on the lamp, then hold down the Shift key on your keyboard and click Lamp Maintenance to select both. Double-click to open the settings window. For lamp maintenance, I'll set the image type to standard. For the foreground color, I'll set it to white, and for the background color, I'll set it to red. For the on state, I'll use the same colors white and red. Now, try toggling the state. You'll notice there's no visible difference between the on and off states. To fix this, I'll adjust the colors further. For the off state, I'll set a darker red, and for the on state, I'll use a brighter red. This creates a noticeable difference between the two states. Once that's done, click OK. Next, I want to add a flashing effect. Double-click to open the settings window again. Under Action Mode, select Flash, and set the device address to Q3. Click OK. Repeat the same steps for the other lamp. Double-click to open the settings, select Flash, and set the device address to Q4. This means the lamp will flash when it's in the on state. Finally, click OK. That's it for configuring the lamps. Next, let's work on the numerical input settings. First, click on the first object, hold down the Shift key on your keyboard, and click on the second object to select both. Then, double-click to open the settings window. For the numerical input, I'll change the plate color to gray. In the Format tab, I won't make any adjustments and will stick with the default settings for now. After that, click OK. Next, we'll configure each input individually. Start by clicking on a single object and double-clicking to open its settings. For this configuration, I want to allow input for only 3 digits, so I'll set digits to 3. Then, under when input value is out of range, check the box to ensure that if the input value exceeds the minimum or maximum, it automatically adjusts to the nearest valid value. Now, go to the Data Over tab and check both minimum and maximum. For example, if I want to allow values between 0 and 300, I'll set the range here. This ensures that any input will be constrained within this range when sent to the device address. Click OK to save the settings. Repeat the same process for the second object D2. Double-click, set digits to 3, check when input value is out of range, and in the Data Over tab, check minimum and maximum, setting the range to 0 to 300. Once done, click OK. Next, let's adjust the size of the numerical input objects. Drag your mouse to select both objects, go to the Format menu, and set the width to 50. Press Enter on your keyboard. Since this width is too small, I'll adjust it to 100. For the height, I'll set it to 60. Now, go to the Home menu, select Text, and draw a text box in your desired location. In the text box, I'll enter duration and click OK. If the text size is too small, double-click to edit it and adjust the size to something appropriate. I'll set it to 22. Then, click OK and arrange the text as needed. To duplicate the text, click on it, press Ctrl+C and Ctrl+V, and position the copy where needed. Double-click on the duplicate and change the text to sec. Click OK, then adjust and align the text appropriately. For the second numerical input D2, click on it and delete it. Then, use your mouse to select and copy Ctrl+C the first set of objects including the text and input field. Paste Ctrl+V a duplicate set, align them evenly, and double-click to rename the input field to D2. This approach is faster and more convenient. And that's it. You've successfully set up and customized the duration section. Arrange the objects and customize them as needed. Then, go to the online menu and select Simulation to test the functionality one more time before downloading the program to the actual device. Once the simulator window appears, click on WindLDR Simulation as well. After the program finished loading, try setting your duration value to 500 and press Enter. You'll see that the value is automatically adjusted to 300 because we set the maximum value earlier. For this example, I'll clear the value and set it to 10 seconds for the first input and 5 seconds for the second input. Next, press the Start button, and you'll see the motor run for 10 seconds before stopping. If I adjust the time to 1 second and press Start a total of 10 times, I won't be able to start it again. At this point, you'll notice that the lamp maintenance will turn on and begin flashing. Once the maintenance for the motor is complete, you can press the Reset button to clear it, allowing the motor to start again. The same logic applies to motor 2. If one motor is already running, the other cannot start because we've programmed an interlock. It seems like the program we've written is functioning as intended. You can now close the simulation and click OK. As for the PLC program, there's no need to save it manually. It will auto-save. Simply close it, and you'll return to the HMI program. Next, I'll guide you through the process of downloading your program to the actual device. First, if you've finished setting up and testing your program, make sure to save your project file. Go to the logo icon and select Save. For the download process, go to the online menu and select Setup. By default, it should already be set to Operator Interface. Under Port, choose Ethernet, and for Network Adapter, select the LAN driver. In my case, my PC is connected to both Wi-Fi and a LAN cable, so I see two options. Be sure to select the LAN connection, as choosing the wrong one may prevent the system from detecting the device. Then click OK. Next, click Download, and a pop-up window will appear. Click Communication Settings again to double-check, or adjust the settings directly, then close the window. Click Search, and the software will scan the network for connected devices. I found my device here. If you're downloading to a new device for the first time, I recommend selecting Download Systems and OS to update the OS to the latest version, which matches your software version. You can download the latest OS from the IDEC website. In this example, I've already downloaded the latest OS, so I'll only check after downloading, execute the ladder program. If you want to clear previous data, you can select that option as well. For the external memory device, if you're using functions that store data on external memory, check each relevant function to download the data to the external memory as well. Then, click Download. Since my PC is not set to the same network as the device, a pop-up will appear, prompting the software to automatically assign an IP address. Click Yes, and the software will temporarily set an IP for the download. Click OK, and the software will begin downloading the program to your device. After that, click Yes to continue the download. Once the download is complete, click OK, then Close, and your program will now be ready for use on the actual device. Please test the actual device to ensure it operates correctly according to the program you've created. This concludes the IDEC FT1J or FT2J PLC plus HMI basic programming tutorial. In this video, I've covered only the basic functions. If you need guidance on advanced functions or assistance with other usage issues, feel free to contact IDEC or your local distributor. Don't forget to like and subscribe to our channel to stay updated with more tutorial videos and new products. Thank you very much for watching the video.